Welcome to Brain Vision.
Okay, so once again, welcome to a new problem involving a spring. The spring has an initial position with a block, and the block has a mass of 4 kilograms on a horizontal surface, which is um, frictionless. So we don't, well, actually, it has friction, the surface has friction, but then we're going to ignore friction in this problem. Um, the spring constant K happens to be 200 Newton meters, and the problem requires that the spring is compressed. So we can have that right here, just to compare the two springs. Well, it's the same spring, but it's being compressed. So this is going to be the new position. This is the original position, x naught, and then the new position would be what we call x1. So the spring is being compressed a specific distance, which happens to be 0.025 meters. So that's the distance the spring is being compressed from this original position up until this final position. So that's the displacement. Okay, that's the displacement. Part A of the problem says that we want to calculate the work involved in during the motion. So the spring is initially compressed, and then they release uh, the spring back to its original position. So I'm just going to have everything lined up there. This is where the spring is, and it's going to take off. So it's going to push the block after it's released. And so we want to find the energy involved in during the motion of the block. So that's the work done by the spring. And also we want to find the velocity or the speed of the block as it leaves the spring. Okay, so those are the things we're working on. Using the work energy theorem, remember that the work done by the spring is the change in the energy or the energy in the spring, which is 1/2 kx final position. I can call it final position squared. Actually, I'm calling it x1, so I don't need to use final position. So let me just use x1. So x1 squared minus 1/2 kx naught squared. Remember, x naught is the original position, which is 0. Okay, that's the original position at 0 meters. So this whole part of the problem will cancel out. And so the work done by the spring is just 1/2 kx1 squared. We plug in the numbers. We have the spring constant, which happens to be 200 Newton meters per meter. And it stretches a distance of 0.025 meters. We have to square that. The final energy of the work done in stretching the spring is 0.0625 joules. That's the work done in stretching the spring. Second part of the problem, I'm going to do that in the next page. We're required to find out what's the velocity of the block as it bounces off the spring. Remember, initially the spring was compressed with the block, and it developed the energy due to the spring, which we called Ws. There's energy stored. We call that elastic potential energy. Elastic potential energy. That's the energy stored in compressing the spring, and then it bounces off. So it's going to go that way. So we want to find what's that velocity when it bounces off. Again, we can use the work energy construct or the work energy theorem, which is the spring is moving. So this is change in kinetic energy. 1/2 mv final, that's the final velocity right here. before it bounces off. The initial velocity v initial will be 0 meters per second, and the final velocity will be v final squared. So this is 1/2 mv initial squared. Since the initial velocity before when the spring is compressed just before it takes off, that's 0 meters per second. So this part of the whole problem, this part of the problem will be 0. And so we already know the work done in compressing the spring from the previous section. If you go back, we found out that it was 0.0625 joules. We're going to plug in that right here, 0.0625 joules. That's equal to, well, actually the best way, like I told you before, the best way in doing these problems is to wait up until the final step. So Ws equals to 1/2 mv final squared, divide both sides by 1/2 m. It's always a good habit to process the problem like that. These two cancel. The 1/2, when it comes up, it's going to become 2. So our v final squared equals to 2, the work done in compressing the spring over the mass of the block. We're looking for the final velocity, so this is 2 times the work done, which is 0.0625 joules, divided by the mass, which is 4 kilograms. And we have to get the square root of that because this is the final velocity squared. So v final, if you plug in those numbers, v final, which is the final velocity, I'll just use my calculator, becomes 2. So square root of 2 times 0.0625, and then we need to divide that by 4, and it's going to give us 0. That's our final answer, 0.177 meters per second. That's the velocity of the spring as it leaves the block. That's the final velocity of the spring as it leaves the block. So the idea is you take the energy, the elastic potential energy stored in the spring, and then that's transformed to motion, change in kinetic energy. The initial kinetic energy before the spring bounces off is 0. And so we're only left with this part of the problem compared to the elastic potential energy. We solve for the v final just based on algebraic simplification. I hope you enjoyed the problem. Feel free to ask any questions or send comments my way. Thank you very much and have a wonderful day. Okay, bye.